Hi, this is Alfozia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is Part 2 video of Trigonometric Substitution. Under the series of integration techniques, this is the topic that we are discussing currently. In our previous video, we had the introduction regarding the trigonometric substitution and we discussed how to evaluate the integral using trigonometric identities and substitution, trigonometric substitution. However, before we move on to more problems, let's first address the issue of definite integrals and how the process differs in this case. In the previous video, we discussed examples without any limits. That's the reason we easily got rid of the absolute value sign there. You can also refer the previous video before starting this video. Okay, let me start with an example. Please look at the question. The limits here won't change the substitution, so that will remain the same. So what substitution we used in our previous example? Yes, x is equal to 2 over 5 secant theta. Using that substitution, the square root still reduces down to, if there is no limit, you can easily get rid of this modulus sign, absolute value bars. However, unlike the previous example, we can't just drop the absolute value bars. In this case, we have got limits on the integral, and so we can use the limits as well as the substitution to determine the range of theta that we are in. Once we have got that, we can determine how to drop the absolute value bars. Here is the limit of theta, and note that if you are not good at solving trigonometric equations in terms of secant, you can always convert to cosine. I am going to do the same thing here. Just plug in the limits one by one, upper limit and lower limit. When x is equal to 2 over 5, when x is equal to 2 over 5 and x is equal to 4 over 5. As I said, I'm going to rewrite this secant theta into 1 over cos theta. You have 2 over 5 on both these sides. So if you multiply the entire equation through by 5 over 2, this will get cancelled out. And if you cross multiply, you will get cos theta equal to 1. Am I right? Same way, let's try the other limit, x is equal to 4 over 5. Just plug in x is equal to 4 over 5 here and solve for the cos theta. Here we have different numbers. Even though I'm going to multiply this equation throughout by 5 over 2. So the 5's get cancelled out and here you'll be left over with 2. Now just cross multiply, shift this cos theta here and 2 here. So cos theta equal to 1 over 2 when x is equal to 4 over 5. Now, we know from solving trigonometric equations that there are in fact an infinite number of possible answers we could use. In fact, the more correct answer for this work would be theta would be equal to 0 plus 2 pi n. Am I right? And theta would be pi over 3 plus 2 pi n, where n equal to 0 plus or minus 1. It will keep on going. Hope you're clear so far. So which ones should we use? The answer is simple. When using a secant trigonometric substitution and converting the limits, we always assume that theta is in the range of inverse secant. Am I right? Or if theta equal to secant inverse of x, then theta will lie in between. Am I right? Okay. Note that we have to avoid theta equal to pi over 2 because secant will not exist at that point. Also note that the range of theta was given in terms of secant, even though we actually used inverse cosine to get the answers. This will not be a problem because even though inverse cosine can give theta equal to pi over 2, we will never get it in our work. So because that would require that we started with the secant being undefined, and that will not happen when converting the limits, as that would in turn require one of the limits to also be undefined. So, in finding the new limits, we did not need all possible values of theta. We just need the inverse cosine answers we got when we converted the limits. Therefore, if we are in the range 2 over 5 less than or equal to x less than or equal to 4 over 5, that is given in the question, then theta is in the range 0 to pi over 3. And in this range of thetas, tangent is positive. And so, we can just drop the absolute value bars. So, let's do the substitution. Note that the work is identical to the first example that we discussed in our previous video. And so, most of it is left out. We will pick up at the final integral and then we do the substitution. Because I'm not going to repeat the same steps that we discussed in our previous example when there was no limits there. So I just move to the answer directly. So if you find the integral, this will turn into tan theta minus theta for the limits 0 to pi over 3, and there will be a 2 outside the integral. So this would give us 2 square root of 3 minus 2 pi over 3. Did you note the difference between the first example and this one? There we were using right triangle to complete the problem. Note that because of the limits, we didn't need to resort to a right triangle to complete this problem. Hope you're clear with this example. In this example, we had positive limits. Can we have an example with a negative limits? So let's take a look at a different set of limits for this integral. I'm going to take the same expression, but I'm just going to change the sign. So here is the example question. Again, the substitution and square root are the same as the first two examples. So we are going to do the x is equal to 2 over 5 secant theta. And we know that the top row is equal to 2 times absolute value of tan theta. So let's next see the limits theta for this problem. So how do we do that? We just plug in the limits one by one in the substitution and get the corresponding theta value. Same concept. We are going to use 1 over cos theta instead secant theta, because that would be easier when compared to using secant theta in a problem. So when x is equal to negative 2 over 5, we get, so this is how we find the theta value when x is equal to negative 2 over 5. Just plug in here, and we know that secant theta equal to 1 over cos theta. If I multiply the entire equation throughout by 2 over 5, I'll get cos theta equal to negative 1. You can also do the calculation part and check. I'm getting cos theta equal to negative 1. So if I take cos theta on both these sides, if I take cos inverse on both these sides, I'll get theta equal to pi. Same way, you can also find theta value when x is equal to negative 4 over 5. So when x is equal to negative 4 over 5, I get, if I plug in negative 4 over 5 on the left side of the substitution, I get negative 4 over 5 equal to 2 over 5 secant theta. Secant theta is nothing but 1 over cos theta. So consider these two. If I multiply the entire equation throughout by 2 over 5, I get negative 2 equal to 1 over cos theta, which is nothing but cos theta equal to negative 1 over 2. Now just take cos inverse on both the sides of the equation. So you'll get theta isolated on the left side, and on the right side cos inverse of 1 over negative 2. So what would be the value of theta? Yes, 2 pi over 3. Hope you're clear till this step. Please remember that in converting the limits, we use the results from the inverse secant or cosine. So for this range of x, we have 2 pi over 3 to pi. And in this range of theta, tangent is negative. And so in this case, we can drop the absolute value bars, but we'll need to add a minus sign upon doing so. In other words, I'll just write it in the equation format. Does this make sense to you? So the only change this will make in the integration process is to put a minus sign in front of the integral, and then the integral would become, steps are same, but we should include negative 2. Now plug in the limits. In the last two examples, we saw that we have to be very careful with definite integrals. We need to make sure that we determine the limits on theta, and whether or not this will mean that we can just drop the absolute value bars, or if we need to add in a minus sign when we drop them. So before moving on to the next example, let's get the general form for the secant trigonometric substitution that we used in the previous set of examples, and the assumed limits on theta. So far, we discussed examples of the type without limits, with positive limits, with negative limits. Hope you're clear till this. So far, we discussed examples with square root in the numerator part, but we also get questions with square root in the denominator part. So if that is the case, you have to do the different type of substitution. Again, for the square root in the denominator, you will be using the Pythagoras triangle when there is no limit. Even for that case, I mean the square root in the denominator, you can have three types of problems: without limits, with positive limits, and with negative set of limits. We are not going to be doing a definite integral example with a sine trigonometric substitution. However, if we had, we would need to convert the limits, and that would mean even eventually needing to evaluate an inverse sign. So, much like with secant trigonometric substitution, the values of theta that we will be using to be those from the inverse sign, or let me give you that. So if theta is equal to sine inverse of x, then theta will lie in between pi over 2 and negative pi over 2. Here is the summary for the sine trigonometric substitution too. Square root of a square minus b square x square can be, for this type of problem you can use the following substitution. X is equal to a over b, this one, a over b sine theta, where theta lies in between pi over 2 and negative pi over 2. There is one final case that we need to look at. We can discuss that in our next video. In case if you get any query regarding this video, please let me know. Thanks for watching. See you in the next